This project is in the field of knowledge representation and reasoning. Knowledge representation and reasoning is a field within artificial intelligence where knowledge and reasoning is modeled using formal logic. We focus particularly on defeasible reasoning, which is a form of reasoning that, in contrast to classical methods, allows us to model information that typically holds, but for which there may be exceptions. For example, we can model statements such as birds typically fly, as presented in the comic. We use the KLM approach to defeasible reasoning, which is based on a series of properties expressing expected characteristics of defeasible reasoning. Within this framework, we can use rules to infer new knowledge from our modeled information. It is often useful to know why particular information is being inferred. For example, in our comic, the one penguin believes, or infers, that it can fly because birds typically fly and penguins are birds. The formal concept associated with this idea for defeasible reasoning is referred to as defeasible explanation. Currently, little work has been done on defining and computing defeasible explanations. It has been shown for classical logics that explanations form an important part of using reasoning systems practically. The concept is particularly useful for knowledge-based debugging, but has also been shown to be important for user comprehension and confidence in reasoning systems. Thus, explanation is an important concept to extend to forms of defeasible reasoning, particularly since classical logics are limited in terms of expressivity, as we will demonstrate shortly. Therefore, the research in our project aims to improve our theoretical understanding of defeasible explanation and propose algorithms for evaluating defeasible explanation within the KLM framework. Before we present the main results of the project, we will first introduce the background information required to understand them. First, I will introduce classical propositional logic, which is used as a base for extension to KLM-style defeasible reasoning. In classical propositional logic, we can encode objects such as penguins and birds as propositional atoms, and use binary connectives to build more complex statements called formulas. For example, the statement penguins are birds can be encoded using the propositional formula penguin implies bird, over here. By modeling our information as formulas, we can build a knowledge base from which we can infer new information. For example, using the information model here, that penguins are birds and birds can fly, we can logically conclude that penguins fly. In classical propositional logic, we use entailment to infer new information. Sometimes we want to know why certain entailments hold. As previously mentioned, for classical logic, this is given by explanations. In our work, we focus on a form of explanation known as justification. Justifications are minimal subsets of statements that allow us to infer a conclusion. For example, suppose we now add the unrelated information that birds have eyes to our knowledge base from the previous slide. The justification for the entailment that penguins fly is given by the statements birds fly and penguins are birds, since this amounts to just enough information to allow for the inference that penguins fly.
So classical logic is a sensible way to represent and reason about encoded information, but it does have some pretty significant limitations. In particular, it doesn't represent knowledge that isn't certain particularly well. So you might want to express that something typically holds, but it may not always hold. So there may be exceptions here and there. And this can limit the level of expressivity of the language, which means we can't always express all the things we want to in classical logic. So a good way to see this is to take our knowledge base earlier, so penguins are birds and birds fly. That obviously doesn't represent penguins particularly accurately, because this suggests that penguins fly. We can try and add a statement here as a particular sort of exception to this rule, but classical logic doesn't cope particularly well with this. In fact, classical logic will conclude that penguins both fly and that penguins both don't fly. And because then assuming that penguins leads to a contradiction, it will conclude that penguins must not exist altogether. And that doesn't work particularly well. As an alternative, we have something called defeasible reasoning, which lets us express what we wanted to say, which is that birds typically fly. So, in other words, this form of logic respects the different levels of specificity of different statements. And the idea is that if we have a more specific statement, like penguins typically don't fly, then that should be seen as overriding a more general rule, such as birds typically fly. So, with defeasible reasoning, we'll be able to conclude that birds typically fly, but also that penguins typically don't fly. So the whole knowledge base essentially stays consistent. So that's all well and good. The next question then might be, well, how does this actually work in practice? So how do we derive the entailments of a given knowledge base? So there are different ways to do that for KLM, but one way is rational closure, and that's the most well-known way. And the essential idea is that we rank the statements in the knowledge base. And the intention behind this ranking is that more specific statements should show up in numerically higher ranks. So you can see here that the statement about penguins appears in a higher rank than the statement about birds. And this statement, which is classical, in other words, certain, appears in the special infinite rank. So I'm not going to get into too much detail on how we actually evaluate this. But once we have this partition of the knowledge base in order of specificity, we can use it to determine whether a certain entailment holds or not. And the idea is that we can keep removing ranks of more general statements until we're left with no more classical inconsistencies. So we mentioned earlier that if we take all of these statements together, then classically speaking, we know that penguins fly and penguins don't fly, and therefore penguins don't exist. For rational closure, we will recognize that for all of these statements, penguins can't exist. So then we try removing this rank, and then we check again. And in this case, after removing this statement, we can reason about penguins classically. There's no classical inconsistency, and therefore we can use the remaining statements to reason about penguins classically in order to achieve defeasible reasoning. So it's also useful to be able to evaluate explanations in the defeasible case, but actually there hasn't been much work in the literature on explanation for defeasible reasoning. So the two ideas that have been proposed in the literature are strong justifications and weak justifications. Weak justification was given as an algorithm for rational closure, while strong justifications are a more declarative and general definition that we apply to KLM. So I'm not going to explain exactly how these are evaluated, but the essential idea is that either weak justification on the left here or strong justification on the right here is identifying statements that are relevant in some sense to the conclusion or the entailment. So that should be clear in this case. If we have something that's asserted to be both a penguin and a bird, and ask whether that does not fly, then we find that that entailment firstly holds according to rational closure, but then these formalisms enable us to identify why, so to speak. So this is the weak justification, and it clearly shows which statements are helpful in drawing the conclusion. The strong justification is similar, but it seems to be a little more comprehensive. And actually, we find this is one of the distinctions between the two formalisms in our work. The strong justifications seem to be a little more comprehensive sometimes than weak justifications. But both seem to be fairly reasonable ways of justifying defeasible entailments for KLM. Okay, so now I'm going to quickly go over our results. Hopefully I've given you some context surrounding what these actually mean. So obviously we don't have the opportunity to go through everything in tons of detail, but the idea is more to give a broad overview. So in my case, I take the definition for weak justification, which was initially just given for rational closure as an algorithm, and see how that applies to relevant closure. So that's the first main result. And then the second main result is that I give a series of properties that are characteristic of weak justification. So the idea is that these properties express intuitive characteristics we expect from defeasible explanation. And then I show that weak justification satisfies all of those properties using proofs. And then in Emily's case, she adapts weak justification to the case of lexicographic closure. So in the same way that this result involves adapting weak justification from rational closure to relevant closure, Emily adapts weak justification to the case of lexicographic closure, another formalism for reasoning within KLM. She then proposes an algorithm for the evaluation of strong justifications in the context of KLM, and specifically for rational closure, which has previously never been explored. We weren't really sure previously how to compute these at all. And then her third main result is she proposes a general definition of defeasible explanation stemming from her work in the other two areas in the context of KLM. So a sort of third suggestion beyond weak and strong justifications.